So now let us discuss electric lines of force. So what are electric lines of force, or also known as electric field lines? Basically, they are imaginary path on which a unit positive test charge moves when released in the field. So if in this region there exists some electric field, then any charge which we keep would experience a force. And now if I am putting a charge over here and it is experiencing force in that direction, then I will say that force is nothing but QE. We had already discussed that. And now we will say that there exists electric field lines which should be along that, right? And if after some time when this charge moves over here and it is experiencing force in that direction, then field lines should be going that way. So they are imaginary lines. They are not actually there. So they are just imaginary lines which are there to explain the field, or to explain the region, that how electric field behaves. So for that we draw some imaginary lines known as electric field lines or electric lines of force. Now let us discuss some properties of them, so you will get better to know them. Now, first property, they usually originate from a positive charge and they end with a negative charge. So this is a positive charge and these are electric field lines which are basically originating. Now where are they going? In case we have only positive charge, then they start from the positive charge and go all the way up to infinity and in all direction, given that only positive charge is there. So this is how field lines looks like due to a positive charge, which is also shown over here. So electric field lines due to a single positive charge looks like something like this, going, they are known to be going radially out of the charge. And what if our charge is negative? Then they start from infinity and come to the charge. So they originate from positive charge, end at negative charge. And if there is positive and negative charge both present, then basically they originate from positive and go all the way up to negative charge. So this is the first property of electric field lines. Next is the number of lines leaving a positive charge or entering a negative charge. Negative charge are directly proportional to the magnitude of the charge. For example, I have charge. I have two charge. I don't know, this is X and this is Y. And they have, like, I have been given a pattern. So here the three field lines are leaving like this. And on Y, there are 6 field lines which are basically entering. So first thing which I can tell is X is what? X is positive charge because field lines are exiting it, and Y is nothing but a negative charge. And what is the relationship? See, it is not compulsory that you draw 3 lines, but if there are 3 lines for a particular charge and there are 6 lines for a particular other charge, then the charge Y has to be twice of the charge X. So I will say the Y is nothing but twice X in magnitude, and one is positive, one is negative. So this is positive, so Y is negative of twice X. So this is how you can relate them. So this is the second property of electrical field lines. Next is, no two electrical field lines can intersect each other. What will happen if they intersect? See, what is electric field at any point represent? So electric field at any point represent the net electric field, which is force per unit charge, and that should be net force per unit charge. So at this point, let us say there exist 2 field lines. One is this field line and other is this field line. Both passes through this point. So this field line is going like this and this field line is going like this. At this particular point of intersection, if you put a small charge Q, then as per our first field line, the force must be along the electric field line, and that is the net force. And as per our field line number 2, the net force should be in this direction. So a positive charge experiences force in the same direction as the direction of electric field line. And now this situation is not possible because a single charge at a single time cannot experience 2 net force. There might be individual force and we can find the net, but as per the situation, both of these has to be net electrostatic force, and at a single point there can't exist 2 net forces, and hence we will say this entire situation is not even possible. So we'll say 2 field lines can never intersect each other. Now next property is, they never form electric field lines, they never form a complete closed loop what will happen if they form the complete closed path? So suppose there is a electric field line which is forming a complete closed loop. Now, if you slowly move a charge from point A to B, C and D and then back to A. So along a one complete loop, if you move the point charge Q, then here the direction of force and the displacement is basically same. So there is a work done, like force times displacement. So work done will be add up. Here the force is in this direction and displacement is in this direction. Here the force is in this direction and displacement is in this direction. So throughout complete closed loop, there will be some non-zero work done by the electric field, which is against the conservative nature of the electric field. If we find the work done in one complete closed path, then that has to be zero. And if it is not zero, means this situation is again not even possible. So electric field lines can never form a closed loop. They always originate from somewhere. From where? From positive charge, or they originate from infinity. And they always end somewhere where either they end at negative charge or they end at infinity. Now next property is they contract longitudinally, that is lengthwise, and producing attraction between opposite charges, and expand laterally, producing repulsion between similar charges. So field lines kind of behaves as a elastic strings which have been stretched and they are trying to compress. So here they are trying to decrease the length, and due to which they will kind of attract, like these will produce the attraction between these two charges, the positive and negative. This is a field pattern due to a positive and negative charge, and this is a field pattern due to two positive charges. So here if they are in same direction, two field lines going in same direction kind of repel each other, and hence they will produce the repulsion between both the charges here. And here two field lines going in the same, here the field lines are kind of trying to contract and here they are kind of trying to expand. So we will say here they are producing attraction and here they are producing repulsion. Now next is the number of lines per unit area crossing a surface at any point, okay, is proportional to the strength, electric field strength or electric field intensity at that particular point. And hence the line of force are closely spaced where the electric field intensity is higher, and it is basically widely separated where electric field intensity is lesser. So look at this case. Here the field lines are moving kind of away from each other. So if we talk about here, the average electric field I am saying is E2 in magnitude, and here electric field is E1 in magnitude. Here they are closely spaced, here they are separated. So this we can say E2 is kind of greater than E1. So here the field has to be stronger and here the field has to be lesser or weak. Now what if they are equally spaced? If they are equally spaced, then number of field line in this region and this region is same. So we will say the electric field in strength in this region and this region is same, and hence that represent a uniform electric field. So field is called uniform if the field lines are parallel, and field is non-uniform if field lines are getting separated from each other or they are moving towards each other. So here as we are moving in this direction, field is becoming weaker, stronger, and here if we are moving in this direction, field is becoming weaker, and here if we are moving in this direction, then field remains same in magnitude. So that's what our uniform electric field is. Now let us discuss the next property. So electric field lines also gives us indication of equipotential surface. So what are equipotential surface? We are going to do detailed study of equipotential surface in our next section. So as of now, we will just say that equipotential surfaces are surfaces which has the same potential. So how potential and electric field lines are related? So we'll say electric field lines are always directed from higher potential to lower potential. Means if this point is having higher potential and this point is having lower potential, then electric field lines will be going in that direction. Alternatively, we can say if we go in the direction of electric field, then potential kind of decreases. So if we are going along the direction of field line, then this region is having higher potential and this region is having lower potential. So this indication is given by electric field lines that when we move in the direction of electric field, potential decreases. If we go in the opposite direction of the electric field lines, then potential increases as we are moving from a point of lower potential to higher potential. Next is in a region where there is no electric field lines, or we can say field lines are absent, the field will be zero. Okay, so if we say there is a region, for example, we have seen this is a positive charge and this was a positive charge. So field lines were going like this. So there was no field line in this region, means the electric field at this particular point is zero. So inside the conductor also we can say electric field is zero. We had derived that using Gauss's theorem. So since electric field inside the conductor is zero, we can also say there cannot be any electric field lines inside a conductor. Next is the electric lines of force end or start normally from the surface of a conductor. So if we have a conductor surface, if it is positively charged, then basically field lines goes, and that has to be perpendicular to the surface. And now after that they can go in any random direction, but when they start from the positively charged surface of a conductor, they start in a perpendicular manner. And if it is a sphere of having a negative charge, then here this is a conductor surface having negative charge, so here field lines will enter, but again this direction also has to be perpendicular. So this is how field lines has to enter or exit. They always have to be perpendicular to the surface. If it is a positively charged surface, then they will exit in a perpendicular manner, and if it is a negatively charged surface, then they will enter with their direction perpendicular to the surface. Let us do a question. So what does this question says? The question says that electric field lines are shown in the figure. This is the region where electric field lines are showing. Now which of the following is correct? Options are that electric field at point A is greater than electric field at point B. Electric field at B is greater. Electric field at point A and B both are equal, and none of these. So first thing is that here in this region field lines are more closer, and more closer means field is bigger over here or field is stronger over here when compared to B. So we will say electric field at point A is greater than, like electric field strength or electric field intensity is greater at point A when compared to point B. So our option is A correct.